Hello and welcome back to another episode of the Oxford MAT Livestream. My name's James and today we're doing past paper questions from Oxford's Mathematics Admission Test from 2016, 2017 and 2018. I'm joined in chat by some of you. At the moment just Aya. Hi Aya. Aya joined chat early just to say hi. We've got a chat moderator who's over there as well, looking after things in chat. Good. Okay. How's everyone doing? I hope you're all right. I think I've pressed all of the correct buttons. Yes, right. Just looking at all of the buttons you could press and try to work out if all of the correct ones have been pressed. If anyone's interested, that's what this feels like from this side. Right. Good. Okay. Here's my plan. Going to do some maths questions. I've picked out several that I think would be interesting to talk about, but maybe you've got opinions too. Maybe there are maths questions that you would like to talk about. Maybe you've already tried the 2016, 2017 and 2018 past paper questions, and there are ones that you find tricky. Or maybe, here comes chat. Or maybe there are ones that you haven't looked at yet. If you're joining in live, then you can ask for particular questions and see if we can do some of those. If you're watching the replay, then you can see if your favourite questions come up, or you can check the MAT Livestream page where we've linked to the kind of standard web solutions for these as well. Hi, who's in chat then? Hi, Anna and Anonymous, and Callie, who's moderating chat. There's Callie, another anonymous person, Yanni, and another anonymous person, which reminds me that you could be anonymous in Slido chat. Let's find out how people's days have been. I always enjoy this. There's a five-star scale for how's your day been today, and you can vote for any of the options, and we almost have one of each. Right, good. Okay, while you're doing that, I think I'm going to talk about one of these geometry questions. Look at this, two things at the same time. That's that's how we do it around here. I can't remember if we talked about this question before the summer in our revision streams about geometry, but just picking up this particular question, it's one of those ones that looks like an algebra question, and maybe you could even do it with algebra and calculus. But it's also got a geometric interpretation. There's a way to do this with geometry. So if you've already seen this question, maybe you've spotted that this thing here, this x squared plus y squared object, should remind you of a circle. And maybe this thing, well, this is something to do with a line where this is constant would be a straight line. So that gives you the idea that you might be drawing some sort of circle. We're thinking about points that are inside a circle of radius 1, and we're thinking about making ax plus by nice and large. So ax plus by equals constant is some sort of straight line, because you could rearrange this to be y equals some straight line equation. I guess with gradient, a line with gradient, if I did that rearranging, so I'd subtract ax and divide by b, like this, minus a over b, seems nice. And I'd like to make that constant large by changing x and y, changing which points we're thinking about. Not ones like this, not ones like this, where they've got smaller values of the constant. I want to make the constant large, because that corresponds to a large value of ax plus by. Slightly brain twisting thing there, isn't there? The relationship between different things. Yes, somebody in chat says they can't hear. Callie is trying to help. Turn it off and on again. It's not me. I think I am making noise. I'm making all the right noises, I think. Oh my goodness. Right, let's have a look at chat as well, because chat's doing stuff. The 4 stars one, there were some people, it was quite a good how's your day vote, I think, but there's a few people who are having a terrible day. I see. I don't know if it's the same people every time who are having a terrible day, or if you're in some sense taking it in turns to have a terrible day. That's one way to think about it, maybe, that all of us at some point are having a terrible day. Maths keeps going. Somebody asked which college serves the best food. I've no idea. I've eaten at some of the colleges, but not all of them by a long way. I wonder if Callie wants to jump in on that. see if Callie's been to some other colleges. Oh, suggestion at the top is to use Lagrange multipliers. That's a technique that I teach to people in tutorials in first year. So if you've already seen Lagrange multipliers, then I guess I don't get to teach that to you later on. you do not need to know what Lagrange multipliers are to do math questions. For example, this one you can do just by noticing that to maximise this, we should be looking for this point over here to make this nice and large, and this point on a circle where we know everything about this problem, right? We know the gradient of this line, so we know the gradient of the tangent. We know lots of things about circles and radii and tangents, and we know the gradient of this particular line and the radius of the circle, stuff like that. Yeah, good. Okay, so I think we can find that point sort of just by doing some trigonometry to think about, or equation of a line stuff. So this line, OP or something. This line. So this line it's at right angles to the tangent. As gradient. Why am I writing it? This gradient. What is this, like 30-degree angle? What am I doing? Okay, let's hang on. Has gradient b over a, because there's this rule about gradients multiplying to -1 if the lines are at right angles to each other, if they're orthogonal. Gradient b over a means it's something like the point P is something like the gradient b over a, the rise over the run, means it's something like a comma b, but not quite that, because that's not on the circle. Maybe it depends on a squared plus b squared, doesn't it? I want the point on the circle, so I think I want to divide that by a squared plus b squared. I'm thinking about the length of a vector. I want distance 1, so I'm dividing by the length of the vector. And then I want to work out the value of ax plus by, which looks like it might be a squared plus b squared divided by the root thing. So I'm going to go for option C. Let's write out some of that. Root a squared plus b squared. Okay, it's not too bad. So that's all right then. And I've picked out this question just to give you an example of one where it's quite hard to categorize this question. Is it a geometry question? Is it an algebra question? Is it a vectors question? Is it something about equations of straight lines? Is it something about surds and square roots and powers, right? Because we have to simplify an expression like this. It's kind of all of those things all at once. And maybe the hardest thing about the math submissions test is that it combines together topics, and you have to decide what approach you're going to use. Some questions might use multiple things. Someone in chat is not allowed to do A-level further maths. That's a shame. A-level further maths is my favourite A-level. And it's because their school wants 9 in GCSE maths. I think I've heard of a case like that before. I can't remember what we recommended. It is easier these days than it used to be to pick up some of the topics from further maths. So if you're interested in complex numbers, then it's easier than it used to be to learn a bit online about complex numbers. There's resources out there to help people with further maths. That's what I'm saying. I has gone for the option where switch to a school where 8 in maths would be your choice of A levels. Oxford's admissions policy is still that 8s and 9s are equivalent to A star on GCSEs. In case anyone was wondering, nobody asked. Nobody asked. As Callie said, Callie's done a reply. Yeah, you can also email me if you would like, or email the undergraduate admissions team at maths. Good. Okay. I've got other questions that I've picked out, so I could just keep doing questions I've picked. Oh, we got through that one really fast. Wow. There was this time a few weeks ago where I didn't do any questions for the first 10 minutes, so now I'm really trying to get a question in the first 10 minutes. Over to you. Here's an interesting comment in chat. Here it comes. Some questions are taken from first year topics. This is maybe the person who wanted to do this with Lagrange multipliers. Their suggestion is that you could solve it through weird methods, but could be easily done by the proper method. I think this question fits into that mold, doesn't it? That you could do this with some weird advanced mathematics. I think there's probably some mathematics super laser that you shoot at optimization problems like this. You shoot the powerful laser at the problem, and then it falls apart, and it's been defeated by powerful maths laser. But in some sense, it's quite unwieldy to use the powerful maths laser when you can do this one using A-level geometry. So, yeah. That up. Where does C come from? Asks Anna. I suppose I'm giving a name to the value of this function. At the moment, I don't have a name for this thing that we're trying to maximize. Maybe you'd prefer it if I gave it a name like something nice like S for this sum that we're doing, ax plus by. If you give it a name, then a natural question I think is where, for which values of x and y, where does this expression take particular values? Where is it 0? Where is it 1? And those questions are, for a value of s, where do you get that value? I guess that's the opposite question, right? To what? The opposite question to what do you get when you plug in a particular value of x and y? The opposite question is something like, for a particular value of s, where does that happen? If you're trying to make s large, then a greedy thing to do would be to say, well, can I make s be 1,000,000? Can I make it be 1,000,000,000? Does that ever happen? And the general thing to do is to say, oh, okay, can I make it 100, 10, 1? What's going on here? And then you start thinking about where is it equal to these different values. It's never 1,000,000,000 for normal sized a and b because you'd have to make x and y really large. I suppose that's the balancing act. This expression is really large if you make x and y large, if a and b are positive. But you can't make x and y arbitrarily large because you're stuck inside this unit circle. Fun kind of trade-off. In general, this is called an objective function. The objective is to maximize or sometimes minimize your objective function. What we're doing here is maximizing it with a constraint to say that, aha, no, you can't just make both numbers 1,000,000,000. You have to be inside this circle. Okay. Oh, answer C. Whoops. You saw that appear in chat, didn't you? I didn't see that. You watching at home, you saw that I was talking about the wrong thing. Right. Okay, answer C. Oh, I did some stuff down here. So we have this unit vector, a, b over this, and I had to actually work out the value, right? I have to take this value of x, which is a over square root stuff, and plug it in here. And I had to take this value of y, which is b over the square root, and plug it in here. It was the value of the function, so I just plugged it in. I don't think I'm doing anything clever. If you notice on the surface of the circle, then yeah, we're working with, once you realize you want to make x and y far away from the origin, then we're working with the circle a squared plus y squared equals 1. I'm going to tidy up my algebra down here because this is very messy. Just for posterity. It says something like ax plus by is equal to a squared over a squared plus b squared. It's not much tidier, is it? Okay. Yeah, good. That simplifies. Go on for posterity, for the stream. A squared plus b squared divided by the square root of a squared plus b squared. I have expression divided by its own square root. That is square root of a squared plus b squared. I'll make this less enormous. Maybe slightly. Bit better. Okay. I'm going to move on. I'm going to switch question. If you have a suggestion for a question, then put your suggestion in chat. But at some point, I've got to talk about the one in the thumbnail. This is a rule that we have. Something has to go in the thumbnail, and then that question has to get discussed on the stream. Otherwise, this was, false advertising. I'm going to give you a second to put things in chat. Let's see how things are going. How are we doing? Yes, we're okay. Doing MAT Livestream. It's a busy week. We've also done Opportunity Oxford this week, which is a bridging program for people who are about to start the course. So we've had people in this week doing maths sessions with us. And tomorrow is an open day. Maybe I'm seeing some people here at the open day tomorrow. I'll see you there. Maybe some people are watching the replay because they found out at the open day that this is a thing, and they're watching it after the open day in the double future. Right, good. I'm going to talk about tan. Nobody's told me in chat to try a different question, so I'm just going to carry on doing this, I think. We've got a complicated diagram, really. The diagram looks like this. The axes are marked cos x and sin x, which is strange. We're asked which of these arcs means something. So graph it directly rather than looking at the unit circle. Which question are you talking about, Anonymous? Sorry, I think I've given you two questions in a row with a unit circle. Or shall you graph it? Maybe I should. Sorry, yes, no, you're asking about this question, obviously. Sorry. Yeah, I would draw some graphs, I think, and then think about the unit circle afterwards. The picture below shows the unit circle. Yes, it does. Each point has coordinates cos x, sin x. That is a bit strange, but then you realise that that is what you would do if x were this angle. And then the unit circle has like radius 1, so this would be cos x and this would be sin x. So x is the angle, and that's a bit weird. Maybe you'd be happier if all of the x's were thetas. I think I would if all of the x's were thetas. I call my angles things like theta. Anyway, we are asked, when is it true that tan x is less than cos x is less than sin x? And we've got some arcs marked on here. For example, option A would be if it's true for 0 up to, I don't know how many degrees that is, but from 0 up to some number of degrees. Is that true? Well, no, definitely not, right? Because look, cos x, when x is small, cos is roughly 1. Let's do a cos graph here. What am I doing? I'm drawing cos x, not underneath chat. There we go. So that's cos. Whereas sine, I'll try and draw it on the same graph, I think, actually. I'll be brave. Goes down to, it's 0 when cos is -1, and then it's -1 when cos is 0, and then back up to 0. Good, this is how you draw DNA. If I then put the lines in, it looks like double helix. Right, okay, the sine looks like this. And to start off with, no, this is rubbish. To start off with, cos is larger than sine, because cos is about 1, and sine is about 0. So not this, so it's nonsense. After a while, I get interested, because there's a crossover, isn't there? At 45 degrees, cos is smaller than sine. So let's think about this. That's where cos and sine are equal. Cos and sine are equal for an isosceles right angle triangle with 45 degree angles in it. So it's 45 degrees. And then they're equal again 180 degrees later. How do you add 180 degrees? They're equal again over here. So I'm only interested in the bit between 45 degrees and 225 degrees. And I haven't thought about tan yet. I haven't thought about this bit, tan being less than cos. But I'm ruling out E, because, well, I guess same reason. Near to 0, cos is 1 and sine is 0, so I'm not interested. Okay, I'm not sure where 45 degrees is on this chart, but something's going on. Sophie's picked option C. Yeah, so subbing in more numbers would be nice, wouldn't it? So subbing in 30, 60. Oh, good recommendations. 120, 210. If you're good at your knowing your values of cos and sine, then you can plug in lots of your favorite values. That's a bit like finding particular points on this graph, here, and I think you're telling me to look over here and so on. I quite like that. That will give us some information about tan x and cos x. Tan x and cos x. We can maybe do better in that I think we can solve this. So when does tan x? We've thought about when cos x is equal to sin x. Now I want to think about when does, oh, Miro has decided not to do that right now. There we go. Sorry, I just shook the screen instead of drawing. It shook the screen in the shape of the letters that I was doing, so maybe you picked up what I was writing. When does tan x equal cos x? Well, it's when sine over cos is equal to cos, which is where sine x is equal to cos squared x. Can I do something with this? Maybe I can do something with this. Maybe think about negative and positive numbers, couldn't we? And what's going on near 90 degrees? Because in the lead up to 90 degrees, tan, I remember now, becomes absolutely enormous, doesn't it? Tan goes absolutely huge, and cos is, it might be relatively large or small compared to sine, but it's not larger than 1, is it? So I think I have issues with this bit. But then this bit looks true, actually. Just after that, I've remembered that tan goes very negative. Graph of tan quickly. Here's tan. Whoop. Up at 90 degrees with sound effects. And then up again to infinity at 270 degrees. So actually there's this moment just after 90 degrees where tan is very negative and this inequality is true. And I think the cos less than sine one is true as well. So I think it's just going to be true. I'm picking C, I think. By the time I get to D, we're at 180, and then I don't really know because that's where tan is 0. I guess cos has become negative at some point, hasn't it? Yeah, maybe we should do this. Yeah, so there's a suggestion in chat that we do 1 minus sine squared x, which I quite like because it converts everything into sines. In fact, that's a quadratic equation, isn't it? So if we let u be sine x, then we get u. I don't know if this is intended for the question that we go and solve this thing, but look, I'm having fun. So yeah, okay. B squared minus 4ac. Yep, divided by 2. One of those looks very negative to me. Root 5 is a bit larger than 2. Minus, maybe they're both okay. Maybe these are both okay. 4 solutions or something. Well, there is a solution of this, isn't there, where u is a bit positive. Do I want that one? Maybe I do. Yeah, there's a solution to this where u is positive, and then sine x has a couple of roots. So this has a positive solution if I take the plus root, which is some positive number. So somewhere between 90 degrees and 180 degrees, as sine comes down again, it's going to go through this value of, what is this? Sine x versus minus 1 plus root 5. Minus 1 plus root 5 all over 2. What a strange constant. So at some point that happens. And then it goes negative, but I've already ruled that out. I'm not interested in stuff after 225 degrees, which happens over here. Am I interested in the negative value? A little bit. Minus 1 minus root 5. Oh no, that's very negative, isn't it? Minus 1 minus root 5. Yeah. Okay, suggestions in chat. Can we also think about using quadrants? Yes, quadrants would be a good approach because it would rule out E straight away if you know some sort of cast diagram, C-A-S-T, or some version of that. You can rule out E. You're going to have a little bit of trouble. Maybe you can rule out A. You might have to think quite hard about A. I'm not sure because sine and cos, well, they're both positive. All three of these things are positive. You might not know what order they appear in that bit of the diagram. The answer is not a quadrant. The answer is something like 90 degrees less than x less than, and then this thing is something like inverse sine minus 1 plus root 5 over 2. And actually I'm not sure I want that one. I think I want 180 minus that, because I think inverse sine is probably going to give me a value between minus 90 and 90. I think I want 180 minus this. Just thinking about, it depends what your definition of inverse sine is. But if you define the inverse function to be, between 90 degrees and 90, between minus 90 degrees and 90 degrees, then technically I want this one in the second quadrant. Yeah, pretty close to the golden ratio, so near. Makes me think that maybe I dropped a minus sign somewhere and that this is actually related to the golden ratio. I guess the golden ratio is larger than 1, so I don't want that. Is this maybe 1 over the golden ratio? Yeah, quick check. I think it might be. Because, here's a fact. Root 5, 1 plus root 5 times 1 minus root 5 is, difference of two squares is minus 4. So I can rewrite this fraction upstairs. Oh, it's got an extra minus sign. So minus 1 plus root 5 over 2. I think there's a minus sign here and there's some extra factors of 2. I think it might be just 1 over 5. Thinking. So I flip it, I get the 4, I get the minus sign, I get the, yeah, okay, that looks true to me. Maybe someone check it on a calculator or something. I think that root 5 minus 1 over 2, the number that's appeared in this question, is just golden ratio to the minus 1. And then this would be the slightly snazzy inverse sine of inverse golden ratio, which is a bit silly. Okay, not really part of the question. Anyway, there's some number out there, so there's some range over here where we're still happy, and then we suddenly become unhappy because we've gone past inverse sine of inverse golden ratio or whatever. We've gone past some point way before we got to 180 degrees, and now the game's over. Yes. Should I go completely non-calculator for my maths lessons until the maths exam? Not sure I'd recommend that. And somebody else asked, should I only do multiple choice questions? Not sure I recommend that either. It's all about having a bit of a balance, isn't it? I sort of think it's good for you to do other sorts of maths as well, not just math questions. I know that I'm doing just math questions at the moment, plus some weird tangent where we talk about the golden ratio, but doing sort of just math questions. Probably good for you to do some other maths. I don't know what that other maths is because I don't know what other maths you're doing in school. Maybe you're on the second half of A-level maths, maybe you're doing entirely further maths at the moment. Whatever it is you're doing at school, maybe you're doing a different qualification entirely. Whatever it is you're doing at school, it's probably good practice for solving other problems. I would like a comparison. Speaking of other sorts of maths, I would like to know about UKMT. I think UKMT is difficult in a slightly different way. UKMT, for those who don't know, is the United Kingdom Maths Trust. They organise maths challenges and Olympiads and eventually put together a team for the UK Maths Olympiad. They're particularly interested in certain sorts of mathematics that are slightly different from the ones on the maths. Matt, if you like, has got more, I think, more stuff on a sort of syllabus, which means we have more kind of expected knowledge that we, maybe that's not true, I don't know. UKMT does a lot of things from sort of no experience needed, first principles. It's going to make things harder. Oh yes, okay, what was this suggestion in chat? There's an algebra in chat. Convert the tan x into sine over cos and multiply by cos. Oh, thinking about positive and negative carefully. Work out whether the sine is positive and find the axis. Yeah, okay. Sounds good. Sounds good. I like that. Anonymous. Yeah, good. Maths 222 has a fact about the golden ratio. It'd be good, wouldn't it? It was exactly 162 degrees. Is that true? That's 18 less than 180. That is 9/10 of 180. So it's 9/5 of a, no. 162, what's going on there? Yeah, something like it's a tenth less than 180, so there's a factor of 5, and then factors of 5 make me think of the cos to the 5 fact, and then pentagons. Right, good, tangent. Okay, what are we doing next? Am I choosing? Are you choosing? How are we doing this? What's the plan? I might be choosing. Okay, if nobody wants to pick a question, then I'm going to keep picking questions. I'm not trying to, I'm just picking ones that I like. Thank you, Sophie. Sophie's picked a question. Hello, Mary. Doing well, thanks. 2016 question 4 is the vote in chat. Let's have a look. Is that the geometry one? That is the geometry one. It's one about circles. Put it on screen. Oh, maths question mark. You've missed a couple of short questions. The recording is on YouTube, but just random different math questions. We're now doing 2016 question 4. You've joined just in time for circles. This question is in radians. Now it's in degrees. What are we doing? We've got facts about circles. The circles are not shown. We're asked about the centres. We're asked to basically say, where are those circles? Where's the centre? Where's the equation? And I think of that as a kind of where question, because I need the centre. I need to know the radius, which is information about where the points on the circle are. So these first two questions sort of seem to say, where is C1? Sorry, handwriting. I might need to tidy up this Miro board. It's currently got all of the past papers in it, and I think that's making it less responsive. Where is C1? Whereas this part of the question, for what value of alpha circles C1 and C2 touch, this brings in C2, which makes me think that it might be about, like, where is C2? And then value of alpha is a circle C3. Good, okay, lots of stuff. Let's see if I can draw circles onto this picture. I think I have a circle tool. We've got a request for 2018 question 4. Maybe after we've done this one. Okay. And then can I move that sideways? Sort of. There we go. Okay. That's my circle of maybe radius 1, C1. And I need a larger circle. Well, I don't need it yet, do I? Because we're just... This is... Oh, sorry. I've used this software for years. How do you do circles? Right, okay. I think I've got it, chat. Here we are. Yes. So centre of circle C1. And I know it's got radius 1. And it's touching both lines. So I should draw these things in. And I could do some angles, right? We've got some right angles here. And we've got something that's 180 minus 2 alpha in here. But I think what I want... Also, by the way, I already know the y coordinate, look. The y coordinate must be 1, because right angle and it's above. And that's made me think about... well, I kind of almost got a right angle triangle. Let's erase this angle in here. I'm not happy with that, because I think what I want is to think about this right angle triangle. Yeah, y equals 1 for the centre. Excellent. Connect the centre to the origin. Two reasons you might think of that. Partly because it says 2 alpha, so you might think about splitting it in two. Partly because the picture's symmetric. There's this lovely symmetry, look, that this line of length 1 goes to that line, this line of length 1 goes to this line. So it's got that nice symmetry to it. Just drawing that line of symmetry in might help us split this up into smaller shapes. I know that people, the answer to geometry problems is sometimes to draw in one more line, and choosing which line to draw in is sometimes the tricky bit, isn't it? Right, what is this then? So, I call this x or something. I guess the axis is called x. Maybe I shouldn't call it x. I'll call it x1 for the kind of distance to get to circle C1. The x coordinate of the centre of circle C1. There you go. And And what do I know? I suppose tan alpha is equal to opposite over adjacent this. So I want something like 1 over tan alpha. I think I don't know the value of alpha. I'm going to work it out in part C, but I don't know it yet. So I think the x coordinate is it 1 over tan alpha? Does that make sense? If alpha is larger, the circle is closer? Because tan alpha gets larger, 1 over tan alpha gets smaller. If alpha is small, then this thing squeezes the circle away really far. Smaller you make alpha, you're squashing it and it's flying off to infinity, being squeezed between these two lines. Okay, yep, I like that. And the equation means that I also need the radius, but they already told me the radius. It's got radius 1. So it's something like this. X minus the x coordinate, y minus the y coordinate of the circle, squared, not plus 1, equals 1. Good, okay, people who drew in this extra line, good stuff, I like it. And already, anonymous person wants to tell me the centre of circle C2. Circle C2 does a similar thing, but with radius 3 instead of radius 1. So I've drawn it like this. Huge circle with radius 3. Missed. Still bad. Not terrible. Okay, radius 3. So in chat, anonymous person, thank you, has told us the equation of circle C2, or at least they've told us the centre, trusting that we know the radius is 3, to write down a version of this with 3's in it, right? It'll be 3 times as large in terms of radius and 3 times as far away, partly, if you like, because we've just replaced all the 1's with 3's in our trigonometry and in our arguments about the y coordinate, but partly because of similar triangles. That if you connect this centre to the origin, you get the same picture but larger. You get a lot of similar triangles. Okay, so if we need it, we've got the equation of circle C2. Now, what we could do is take those, we've got a choice, I think. We would like circles C1 and C2 to touch. I can think of a couple of ways to do this. Maybe you could let me know in chat. Have I got my coordinates the wrong way around? There's 2 people in chat, maybe it's 1 anonymous person twice. No, I think I'm right. I think 1 over tan alpha is the x coordinate, I think. Okay, it hardly matters. Well, I think my picture might be the other way around from yours. Yeah, so suggestions about how to implement this idea about the circles touching. We've got this kind of statement in words that the circles touch. I'd like to turn that into maths. And there's several different ways, I think, that we could do that. So if you've got an idea at home, let me know. I can see one idea has appeared in chat. I would like, for diversity of approach, I would like it if chat could have a second method as well. I'll read out the first one while we're waiting for a second idea to appear, which is something like, if you find the distance between these 2 points, where you know exactly where those points are, if you find the distance between them, then we've got pretty strong feelings about what that distance should be. The distance should be, for the circles to just kiss, should be 1 plus 3. This is this circle pointing a little radius out in the direction of the other circle, and this is the big circle pointing a radius out in the direction of the small circle, stretching just the right direction. That's the point where they're going to meet. And if at the point where they meet, the distance between the centres is exactly 4. The distance between the centres of 2 touching circles. Yeah, and then a separate approach. Love it. Good. Yes. And we've got a third. Excellent. And in chat, they're already calculating the distance using, I hope, Pythagoras, which they're going to rearrange. Good stuff. We've got a second method, though, which is to think about the trapezium. That if these circles actually touch, then they form a trapezium, or the centres and the points of contact form this trapezium with So at the moment they touch, there's kind of I'll draw in a little bit. There's the point where they're meeting. That's got length 4. Sorry, that bit was supposed to be the circles, but the circles are hardly relevant anymore. Lots of right angles, and possibly we also know, we know everything. So we can calculate loads of stuff now. We can work out this height is 2. We've got some angles. You know, you name it, we can mark it onto the picture. Opposite over hypotenuse, some sort of sine. I think this angle is alpha, so sine alpha will be 2 over 4. I have strong feelings about that angle, so that's quite nice. And I suppose that's using the distance fact. Alternatively, so trapezium method I quite like. I have to draw this trapezium, and pleasingly I get to mark the lengths 1, 2, 3 and 4 onto my diagram. 1, 2, 3, 4. Distance between those coordinates, I like that because we've found some coordinates, and now we want to set the distance equal to 4. I'll just do that algebra down here just to demonstrate what that would be like. So we have the points 1 over tan alpha, comma 1, and 3 over tan alpha, comma 3 should have distance 4 between them. So that's the difference in x coordinates, 2 over tan alpha, squared plus the difference in y coordinates squared should be 4. What have I done wrong? What have I done wrong? Because those 4s are going to cancel, and then I'm very scared. Tan alpha infinity or something. What have I done? Chat, help. Help. Opposite of adjacent. Being really silly. Right hand side needs to be squared as well. Yeah, squaring distance. Pythagoras involves a square root. Thank you, chat. Thank you, like 3 people. Don't use Pythagoras, that introduces the square root. I'm sort of using Pythagoras, but I've squared the right hand side. I have now that I've been told. Thank you, chat. Genuine error, not a. Yep, thank you, there it is. That was the one that I understood. Yeah, should it not be 4 squared? No, it should be 4 squared. I'm wrong. But I knew I was wrong because I was about to get something stupid like 0. I think I've just scribbled out 12 and I was about to write 12. Let's integrate that. 16 take away 4 is 12. So 4 over tan squared alpha must be 12. So then 3 is tan squared alpha. Rearrange this, rearrange. Tan squared alpha is like 1 over root 3. I have strong feelings about this angle. Try and work out what the angle is. Okay, so that's what the algebra would look like if I got it correct. Using Pythagoras. The square root is lovely and gives an exact value. Yeah, sure. Okay, you can take this square root. Okay, I had another approach, and I saw someone say set the equations equal to each other, which I think is genuinely a different approach. Let's work it out just because we can. We've now got 2 successful approaches, right? So let's go for a third. So this is something like x minus 1 over tan alpha squared plus y minus 1 squared is 1. And then circle C2, we decided it's just 3 times further away from the origin and 3 times larger. So the idea is maybe we could look for points on both curves. Should be exactly 1. And these are quadratics, which gives me hope that this could turn into a kind of quadratic equation question, looking for exactly 1 root, a kind of repeated solution. I suppose I would have to maybe plug one of these into the other, or I think I'd prefer to take the difference between these. Yeah, I think I'm going to take the difference between these equations because that cancels all the quadratic terms. The x squareds and the y squareds look kind of similar in both equations. So if I do the difference between these, it's not going to be the most beautiful algebra I've ever done, but this is coming from someone who just forgot to square 4. I think I was thrown by the fact that 4 is already a square number. Square it twice? That's madness. I should not. Squaring 1 over tan alpha minus, I've got to subtract 9 over tan squared alpha. I'm slightly regretting this. I've missed the factor of x that appears in these two terms from doing the cross multiplication. Squares, but I'm subtracting that one. There's a minus sign for multiplying out to get 6, but subtract it. Similar thing over here for the y's. Oh, it's not too bad. Y squares cancel, minus 2y. Minus 2y, subtract 6y up here. Plus 1 minus 9 is 1 minus 9. So some of the 1 minus 9's cancel on both sides. There's a 1 here and here. There's a 9 here and here from squaring. Oh my goodness. Yeah, we're hoping for a b squared minus 4ac kind of situation. This is going to give me a relationship between x and y. It's not nice, but that is what it is. So this is 4 over tan alpha times x minus 8 over tan squared alpha is plus 4y is equal to 0. So this gives me some fact about y. Oh, with loads of factors of 4 in it. And a square? No, no squaring. Just the y, just factors of 4. Divide it by 4. I'm starting to have mixed feelings about this method. Oh no, I'm not. It's got a y now. I'm happy. Take this expression for negative y, plug it in here, multiply out, get a quadratic for x. You want one solution, write down the discriminant. Might not do all of this on the board. But the plan, I suppose, just to draw some arrows, right? If in doubt, draw some arrows. The plan is to take this, put it back in here with a minus sign, multiply out, get a quadratic for x. Oh, I've done some of my writing underneath chat, haven't I? But it hardly matters because it's such a mess. Quadratic for x, write down the discriminant. That's a b squared minus 4ac kind of situation. That should be 0. That one feels like the most work. It is equal to 9. Good spot. Thank you, chat. That's the 3rd time in half an hour that I've mixed up equals and plus. And they are the same key on the keyboard, but I'm not a keyboard, so I don't know what's going wrong there. Okay. I don't get equals and plus the right way around. Okay. Fun times. We've done 3 methods, I think, for getting these circles to just touch. Part 4 is my favourite part of the question. Part 4 says, for that value of alpha, a 3rd circle, larger than C2, is drawn between L and the x-axis, and that one touches both lines and also touches C2. What's the radius of this enormous circle? And the answer is just 9. I'd like chat to have a go at explaining why it's just 9. I mean, you can do all this sort of algebra again. You can do another picture of a trapezium to explain how that circle, this huge C3 circle, is tangent to C2. Draw another trapezium, off you go. But maybe chat can have a go at telling me why it's just 9. Yes, I agree, by the way, that I think that trapezium method was the easiest one for me to draw on the board. In terms of, it's only an easy method for you if it's something you thought of or something that you feel you would think of it. Actually carrying it out, fine. Also got to have the idea that you want to draw that in. And crucially, I'm going to highlight it again. I had to draw a line in, right? I had to draw this horizontal line in. I suppose I drew that one in because I had some parallel lines and I knew the heights of 2 line segments. So I can mark in this and I'll be okay because I know some information. I know the difference between those heights. I knew this height was 1 and that one was 3. So drawing this in meant straight away I could label a couple of things, square roots and 2, rather than just being a random line in the middle of nowhere. Drawing this line in let me label alpha straight away and made a little triangle. Making triangles is good in general. Ooh, what's this? 1/2 is r minus 3 over 3 plus r. That sounds like a trapezium argument to me. I've done some sort of picture of a trapezium. I like that. You can rearrange that equation to get r is 9, because then 6 over 12 is 1/2. Well, it's quite a good algebraic exercise. I quite like that. X minus 3 over x plus 3 is equal to 1/2. Find x, 6 over 12. Guess you could sort of simplify this expression, couldn't you? When you see something with x upstairs and downstairs. Something like this, maybe. Now it feels more complicated. I guess I'm in the process of inverting the expression. So 1/2 divided by 6, get a 12, flip it upside down, get a 12, subtract 3, get 9. Nice little problem though. Good. I've come back to writing at 30 degrees. Is it 30 degrees in the question, by the way? I think it might be 30 degrees. I've sort of lost track of all the angles and things. Where am I? I suppose I should think about sine alpha being 1/2. Yeah, I think it's 30 degrees. And I like the similarity argument a lot as well. If you like similar triangles, there's a similar argument again to say for this value of alpha, we've shown that that corresponds to a circle of size 3, a circle of size 3 being tangent to a circle of size 1. If you scale up the whole picture, you'll get a circle of size 3 tangent to a circle of size 9, because 3 squared. You could keep going. Question doesn't ask you to, but you could keep going. The next one's got size 27. The one after that has radius 81. There's a geometric series here. Brilliantly, it's a geometric sequence because of the geometry of the problems. That's why it's called a geometric sequence. Who's got r as minus 3? Oh no. Oh no. Minus 3. Fair enough, I think. Because minus 6 divided by 0. No, don't do it. Resolution 1 minus 3? No, I suppose not. There's some diagram dependency then. So this doesn't... I guess we should be able to get back to the circle of radius 1. Maybe it flips some plus and minus signs. 4 over negative 2, something like that. If you flip some plus and minus signs. To get back down, if you had a large circle and you wanted something that was smaller than it, then I think there's a standard sort of scale factor argument for that as well. Someone in chat's got A in additional maths in IGCSEs. GCSEs are something we look at where you've got them, but we're also interested in what you've done since then. At the time you apply, it's usually about a year after you've done your GCSEs. You might now be on track for the top grade in whatever you're doing next. So we know that there are a big collection of exams you do a year or so before you apply to university, but by the time you get to university they're 2 years away usually. So we look at them, but we'd obviously prefer it if people had top grades in the exams that they do, because that shows that you're good at getting the top grade in exams, but it's not as important as things like the mathematician test, which is why I'm doing a MAT livestream and not a IGCSE livestream. I guess maybe there's an overlapping content anyway. Right, I do worry a bit about this person who's got r equals minus 3. Radius is positive. Good. What are we doing in the question? I've sort of lost track. I'm having so much fun with the geometric sequence that the answer is just 9. Do I need to do something else? Oh, it asks for an area at the end. Oh, this seems a little bit like, it's extra work, isn't it? Same value of alpha. The area of the region bounded by the x-axis in circles C1 and C2, they are tangent at this point. So I suppose I need to draw a diagram where I have my circle C1, draw a circle. Working out which area I want is the tricky bit. I need a circle that's 3 times as large, more or less. That'll do. That to be kind of tangent. I know some angles around here as well, but what area do we want? Is it this one between everything? X-axis, C1 and C2. Yeah, it's this kind of curved region. region with two curved sides, like a kind of weird triangle. Okay, so I guess there's some bit of circle here, some bit of circle here. I'm drawing the trapezium again because it was helpful before, and because when you see a bit of area with a circular arc in it, finding the area outside the circle is often quite tricky. Finding the area inside the circle is often quite nice. So if we could do something like the area of, I'm going to draw the same picture again. If we could do something like finding the area of this triangle plus this rectangle for the trapezium, and then allow for two bits of circles, I would do something like that. I would do rectangle plus long triangle minus wedge on the left minus wedge of a circle on the right. I should color code this. I'm going to color code this while you tell me what we're doing. 1/3. Oh, is it 1/3 because it's 120 degrees? 120 degrees? I suppose there's a 30-degree angle and a 90-degree corner, so I shouldn't be that surprised. This is terrible color coding. I really missed with that pink line. Let's just pull pink line out. Forget that. Pink rectangle plus a blue triangle, that's how I make a trapezium. Some people know this formula for the area of a trapezium. I never trust myself to get the formula right, and it's not that hard to build your trapezia out of triangles and rectangles. And I need one more for this bit over here. Can I colour that one in? Sort of want to colour that one in. I don't want this area, so I'm going to shade it. And remove this bit. And remove this bit to leave this sort of bit here. Tricky, when you draw the diagram, there's this tiny little region here which could confuse you. If you have 30 degrees looking like quite a small angle, then this point is going to be very close to these 2 points in this bit of line. How are you doing IGC? You're doing your IGCs and you're doing the other stuff as well. Oh, there's the formula for the area of a trapezium. I've seen it before. Yeah, so you've got to identify the two bases, which in this case awkwardly are the sides. Upper base, lower base. I don't think I've heard the phrase upper base before. Maybe I wasn't paying attention when they told me about trapezia. Times height divided by 2. Okay. And I know the height from a previous calculation, probably. I think. So 1 plus 3 times the height, which is this width on the picture, which I know from previous parts like 2√3 divided by 2. Okay. Maybe this is what people in chat have already got for this. Good. Okay. Oh, I'm pleased with that. That's some colour coding. And I've slightly circled a bit of a question, so that's convenient. That, to me, that reads like an extra bit of the question that's been added on, partly because the previous parts are not too bad. I don't know. And, you don't really use the information. I guess you use the diagram. You use the diagram and you use the value of alpha. You've got to know where stuff is in order to do that area. Maybe that's the point of the question. Maybe that's the point of the question. Draw this thing with this thing. The question's got a slightly funny structure going on, right? That you don't know alpha, and then but you do know that you want 1 and 3, and then you work out alpha from that. You can imagine doing this where you know alpha and 1, and you know the fact the circles are tangent, and you find the radius of the larger one in terms of tan alpha. It's sort of slightly odd that the question introduces alpha and then kind of locks it down. In about part 3, alpha gets locked down to a particular value, when I think you could do most of this question in general, restricting to the 30-degree case. So anyway, never mind. If you want extension, try and, I suppose the obvious extension is to try and do this in general, where I suppose instead of 3, you're told it's capital R, and then you have capital R's throughout the rest of your question. And maybe that lets you then have fun, like varying the value of R to see what happens to the size of this area. I don't immediately know what happens to the size of this area. If R is very large, then the line must be very steep. So probably the area is tending to a constant or something. Could be interesting. If r is very small, then if it's very close to 1, then this line is almost parallel. So the area is very far away, but I think the region is very far away. The area is probably tending to a constant. Some sort of interesting r equals 0, r equals 1 kind of case. Anyway, never mind. I've gone off on a tangent talking about tangents. There are requests for a couple of 2018 questions. Ooh, what's this? Oh, it's a final answer. 4 root 3 minus 11 over 6 pi. Sounds right. Yeah. This 5v. Oh yeah, not a silly question. Before we move down to 2018, we've got some requests for question 5 and then 2018 questions. I've kind of ruined this a little bit by circling it, so I'm just going to move my diagram. I'm very pleased with my diagram. Okay, let's group that. Oh, that's made it very ugly. Right, let's just move that down a bit. Okay. So this bit in here, in part 5, somebody asked about this k. This whole question is about a kind of sequence. They call it a sum, but I mean it's got a subscript n on, and we're going to change n, so that's a sequence for me. So you have like a value of s1 and s2 and s3, which I think is 34. You have some values of these things. We're asked to find the sum where k is a variable that's going to go from 1 to n, and we're going to add together the values of s subscript k. So we've got this sum like this. So that means s1 plus s2 plus s3 plus ... plus sn. So add them all up. It's a subscript k because s itself is a sequence with subscripts in. The joke here, I suppose, is that s is already defined as a sum, so you're doing a sum of sums. But it's not too bad by the time you get down there. Yeah, if 2 alpha is greater than 90, everything goes inside out. No, that's not true. That's not true at all. That's just some nonsense I've said. Oh dear. I need to think more before saying nonsense like that. I think we did this question before summer because I remember writing an extension for it where you did the sum of the sums of the sums, which was a mistake because when I write an extension question, I have to also do the extension myself. And it was terrible. I almost deleted the question, it was that bad. The extension question is not part of the MAT question. The MAT question is fine. This one's a little bit fiddly perhaps, but it's fine. So I think we've discussed this one on the live stream already. I'm going to point you to a previous episode, I think, on sequences and series, which was, several episodes ago on this YouTube playlist if you're on the playlist, on this channel if you're just on the channel. If you're watching this in some sort of strange YouTube thing where there's recommended videos, then click on them at random until you get eventually to the one that I'm talking about. Hopefully, good luck. I don't know if YouTube recommendations work like that actually. Maybe it's like Wikipedia and you end up in a loop. Someone should test this. If you always click the first recommended video, do you end up seeing everything or do you get stuck in a loop? Do you get to just one video that recommends itself, a fixed point? Are there 2 videos where you're recommended to watch the other one in a loop forever? Right, it's 6 o'clock. I'm going a bit silly. If you've been looking at a screen for the last hour, remember to look away from the screen briefly. It's good for your eyes. Really, I think you're recommended to take breaks every 20 minutes or something like that. If you've been doing maths for an hour, then let's all quickly think about something else. That was nice. Right, okay, so this question, we've talked about it before, I think. The tricky bit is part 4, to work out how these things are related to Sn. Tn here has the n's going backwards. You have to be able to find a copy hiding in here somewhere of 2, 8, 24. And after looking for ages, you notice that these things multiply to -2, these things multiply to -8, and these things multiply to -24. So if you multiply out all the brackets, then you get the sum that we had before, plus some sort of geometric multiple of n. Yeah, good. Okay, and then this one is just, I think, the previous one divided by 2 to the n. It's been a while since I saw it. Yeah, it is. It's the previous thing divided by 2 to the n, but the term's written backwards. So it's just 2 to the n over 2 to the n. which is just daft. By the end of the question, it's daft in the sense that once you've spotted it, you're kind of done. You don't have to do any algebra or anything. Before you spot it, it looks terrible. Part 5, by the time you get down here, you have an expression for the sum. You know that the sum itself involves things that look like n times 2 to the n. And the key idea is that when you're adding things that look like n times 2 to the n, that's precisely the definition of Sn itself. So in this weirdly circular way that actually makes sense, when you're adding these values, you're adding up 1 times 2 to the 1, 2 times 2 to the 2, 3 times 2 to the 3, 4 times 2 to the 4. That's what Sn is. So okay, there's a factor of a out the front, and we've also got to deal with this term and that term, but this tricky one with the n 2 to the n in, we have a definition for that. That's Sn if you add up the first n terms of this sequence. Sk if you add up the first k terms. What are we doing? We're adding up the first n terms. Adding up the first n terms, that's Sn. And then we know a formula for Sn. Here it is. So you've summed the formula, you get the formula. It's weird, with different constants in different, slightly different terms, but the sum of these terms is sort of the same thing as the definition of these terms, which is nice, really, isn't it? Oh, is that a video for the series and sequences? Thank you very much, anonymous person. That's very kind of you. It's a live video, so it's probably not. It's probably not Rick Astley, but no, I think that's sincere. We're going to take that as a YouTube link. Okay, down to 2018, I think. I thought we might talk about this horse question. There's a horse. It's in a field. Could get some grass. I don't know. You can request the horse question in chat if you like, I suppose. I think there were requests for question 4 and question 5 on 2018. Look at this diagram. Look at this diagram. The diagram is complicated because it's a diagram for all 4 parts of the question all at once. The point E and this dotted line aren't relevant until really late on in the question. And if you delete the dotted line and point E, then you might as well label root 6 over here instead. You might as well label the radius, instead of labeling the radius from B to D, you could label this radius from B to C. So there's a version of this question where the things that are labelled are like A to B is radius 2, B to C is radius root 3 minus 1, weird number but okay, and A to C is length root 6. That's radius of a circle. That's the kind of relevant triangle, ABC. And we're asked for the angle CBA, which is this thing here, which is just going to be the cosine rule. So being able to extract the right information from a complicated situation and draw perhaps a simpler diagram for that part, that's a useful skill to have, I think, for lots of sorts of mathematics and maybe the real world as well. People are giving you too much information these days, I think. That's not a political opinion. People are giving you a lot of information these days. Being able to extract the relevant information is important. Gosh. Okay, it's not that bad. Once you draw out the relevant information and draw out the relevant picture, maybe you can do that. So this angle is larger than 90 degrees. So A and B lie on the same side. It's not the case that this is a small angle. They're on either side of the line CD. I guess I've read the previous bit of the question. I'm not just relying on the diagram, but that line CD is at right angles to AB because of the kind of up-down symmetry of this. Equal distances, isosceles triangles, right angles, that sort of stuff. Yeah, we had the cosine rule. It was good. I liked that bit. I think it might even be something nice, like 120 degrees. Shall we work it out? Let's work it out. We haven't done the cosine rule for a while. Here's a triangle. We're going to find out this angle theta using the cosine rule. Now I know some people have memorized the cosine rule both ways round for speed or something. I only know the cosine rule one way around, which is to write out c squared is equal to a squared plus b squared Oh, attempting to square that in my head was not a good idea. Minus 2bc, am I going to do it again? 2bc cos theta. Sorry, just trying to egg myself on as I try and rearrange these square roots. I thought this would be a nice number. I'm willing to accept that I may have been wrong, because I'm going to subtract this. What is this? Minus 2 plus 2 root 3. This looks awful. 4 root 3 minus 1 cos theta. This is not good. So this is 2 times root 3 minus 1. This is fine. This has almost immediately gone from terrible to fine. Cos theta is 1/2. I have strong feelings about that angle. Do I mean minus 1/2? Where's my dropped minus sign? I dropped a minus sign somewhere? Maybe not. I would like it to be larger. I'd like it to be 120, I think. Lovely chat. Can you bail me out again? Where's my minus sign gone? Ooh, minus, there it is. Found it, don't worry, found it. It was here. Minus 2bc. I wrote it down and then I lost it in between the lines. The more lines you use, the more minus signs you can drop, but the more things you try to do in your head, the more minus signs you drop. So they get me both ways around. So there was a minus sign in here somewhere. So this is minus 1/2. So theta is 120 degrees. After I found my minus sign. My clue was that the very next thing I'm supposed to do is to say that the angle is bigger than 90 degrees. So I should probably get an angle that's bigger than 90 degrees. Am I going to be at the open day? Yeah! We've spent quite a bit of time this week planning the open day. There's a maths at Oxford talk that I'm doing at the open day twice tomorrow. It's going to be good fun. You can go and see some colleges as well. Maybe visit computer science. It's going to be great. If people are watching this where they can't make it to an open day, don't worry. All the information on the open day is in the prospectus, and you're welcome to contact us by email if you have any questions. Email address in the YouTube description, and pretty easy to find on our website. You can also, somewhere on our website, on the open day section of the departmental website, you can find recordings of a previous online open day we did. Somebody is very keen to know if I do any interviews, and I do interviews most years. I think I'm interviewing again this year. I don't interview everyone, that would be mad. I interview some people as part of a team. Good. Right, what are we doing? Somebody's asked me to do this geometry question, which has got lots of parts, and look, the answers are all things like this. Pi multiplied by root 3. Ugh. It's really unpleasant. Let's go. So CD has length 3 minus root 3. So for this part, I want to draw a triangle that has the line CD in it. My previous symbol diagram didn't have the line CD in, but I think I do want to draw this. And I need some inspiration, so I'm going to mark in some more angles, I think. I've got this angle that I already know is 120, not 60, because I found the minus sign. I'm sort of hoping that there's more nice angles. Up-down symmetry seems like quite a big thing in this picture. It's reflection symmetry in the x-axis through A and B. So maybe I draw this one in. This will also be 120 degrees. And then maybe I'll get 120 degrees over here, and then I'll be done. That would be nice. So I know this length is root 3 minus 1. This length is root 3 minus 1. I've already done this up-down, switching from this line BD to the line BC for my picture over here. So maybe I'm already thinking about up-down symmetry. I could probably do this with the cosine rule. Now that I know the angle, I think I want to do something more like 60 degrees, split it in two. Both things work. So then this is root 3 times as long as that one, which is 3 minus root 3. Good. Hence calculate the angle CAD. Oh, that's all right. Okay. Because I know, oh goodness, so many triangles. Angle CAD, I want a triangle with C and A and D in it, but I know the length CA. I know the length CD is now 3 minus root 3. And I know the length DA because that's another radius of the circle centered at A. Drawing my own diagrams here to split out the important bits of the picture looks mad because I've now got 4 diagrams on the go, but on the other hand it's how I can bring out the bits that I'm being asked about, and I suppose I'm using my skills of like recognizing, given this particular information, I've got 3 sides and I want the angle, and I can't spot that. If I just draw in here some angles, then I've got so much going on that I don't know what to do. You know, angle at the center, so I should look at the angle over here somewhere or something, but no, I should not do any of that. I should just pull out the triangle where I know all 3 sides and try and think about the angles. This angle is also nice. You do not need to dress smartly for interviews. Anything that's comfortable. I'm not going to be wearing a suit when I do interviews. I'm going to be wearing this, to be honest. Not like I'm just wearing the same clothes between now and December. That's my plan. It's online though, so that's going to be fine. Sine law, yeah. Oh, so angle CAB. That's clever. Sine law to find angle CAB. That's a good idea. I like that. I don't go for the sine. I don't go for the sine rule as often as I should. Maybe I should go for the sine rule. Let's give it a try. Sine theta over root 6 would be sine phi divided by root 3 minus 1. Yeah, that's quite nice. I like that. Because I know sine theta, there's 120 degrees, so sine theta is root 3 over 2. And that cancels nicely with this root 6, doesn't it? Well, not quite, but almost. It's not perfect, is it? Root 3 minus 1 over 2 root 2. I don't know what the angle is. That's a shame. That's a real shame. I don't recognise that sine angle. Maybe I've done a typo, but I think it just might be something weird. It looks like I've got root 3 minus 1 over 2 root 2. Sine theta, definitely what I mean. Sine 60, sine 120. Is it root 3 over 2? Yeah. Half the triangle CAD and then use SOHCAHTOA. Yeah. Oh, split it in 2. Like this. This is the same argument, isn't it? Oh, but you've got a right angle triangle, so you could do SOHCAHTOA tricks. Ha! That's very nice. Look at this. Look at this question. This question is great. At James, do you want me to call you James? Yeah, that's fine. Everyone calls me James. How long are interviews? Are normally about 20-25 minutes, something like that. Some colleges might do half an hour. Some colleges might stick them together and do something more like 40 minutes. Usually about 25 minutes from personal experience. Interviews before results. Yep. So interviews. We do our interviews in December, early December, and that is before results, because we kind of believe that you're just going to get the results that you need. But we do check. So the way it works is we interview and we decide who we're going to make offers to, which is not everyone we interview, but we decide who we're going to make offers to. And then if you've got qualifications outstanding, we say, sure, you can come to Oxford, conditional on get such and such grades in the exams. And for some people, if you're doing international A-levels, I think you might have already done the exams by that point, so you might get your results straight away in January, or you might even be holding them when you get an offer from Oxford, in which case you just say, yep, done that. While you were thinking, I went and got those grades already. And for a lot of people, they do their exams in June in the summer sitting. So for a lot of people, they stay in school or keep learning A-levels or whatever, or equivalent qualifications, and then take those in June. But yeah, if you're an international student, it is a little bit strange that you apply with predicted grades for an exam that you are just about to do. But for Oxford admissions, it hardly ever matters, because you predicted some grades and then you get those grades. Good, right? That was. But don't worry, the open day tomorrow. If anyone's coming to the open day, I'm going to be much more eloquent. I'm going to be much more useful than get the grades. Although, wouldn't it be fun? Wouldn't it be fun? Wouldn't it be fun? Not saying anything. Sophie's interviewing Callie about interviews. Callie is a current student who's now going to say how many interviews they have. It varies a little bit from person to person. Oxford math students usually have at least 2, sometimes more. Am I going to do these areas? I think by this point of the question, once you've got some angles on the circle, we've done a lot of these questions where you have bits of circles and you do the difference between 2 areas, that sort of thing. It's not too bad. The last part is pretty strange. I've never seen this. Is that true? I've maybe never seen this on a math question before or since. It's the idea is, I'm not going to read out the question. The idea is just that as you move the point E, the line, what are we talking about? The line CE sweeps out, the line CE changes as you move the point E. So if you move it around, the line CE changes. If you get all the way around, then you have almost no area on one side and almost all the area is on the other side, area of the stuff inside this picture. If you put E all the way over here on the other side, you get almost no area on the other side. So somewhere in between, it's done 50-50. You know, it's gone from being lopsided one way to being lopsided the other way. Somewhere in between, it was perfectly balanced, which is something called intermediate value, and it's a thing you learn at university. I guess it's also intuitively obvious that this thing goes from being all on one side to all on the other side, so somewhere in between, across 3. Do not integrate it. Oh my goodness. Look at the shape. It's horrible. Don't integrate that. It's like parts of circular arcs and bits of circles going through extra points. Don't integrate that. Wow. Oh, terrifying. Look at all the exclamation marks, though. I think it might be sarcastic. Ooh. Good. Okay, that's what I have to say about this question. Ooh. But seriously, though, the last part is about the kind of perfect balance between extremes. It's not about calculating this. You write down an equation, but then you write down an equation, but we're not going to solve it. So you write down what would it mean for half of this to be something on there. So I suppose in terms of x, we write down an expression for the area on one side of the line. Probably this left side, it looks nicer. So an expression for that area. We do not actually solve the equation because that would be mad. Okay, so question, one of those questions that looks really scary and is millimeters away from asking you to do a very scary thing, solve that equation at the end. But actually the things they're asking you to do, if you draw separate pictures, split it apart, then you can attack it bit by bit. Right. Okay. I think there was a request for question 5. Or maybe it's one of my picks. It's towers. Look, I want to talk about towers. This is one of those recursion questions. I do like a bit of recursion. So here's what's going on. Lots of definitions at the top, but not too bad. A little bit like an interview question, really, in that some new things are introduced, and then we have to do some activities with them and maybe build something iterative along the way. Right, okay, good. Is this iteration? Maybe it's not iterative. Oh no, there is a formula. There's a formula down here. We're okay. Draw the other 4 towers means draw things where you have bricks on top of that. The rule for the bricks is that they have to add up to size n if they're sitting on top of a brick of size n, so maybe 2 plus 2. And then on top of that, you keep going until you get down to 1 bricks. Yeah, because 2 other towers are stacked, a K1 tower and a K2 tower. And yeah, so a 1 tower has its own special definition. It's a 1 brick. So the 1 tower is just defined to be this and stop. And I can do that here as well. And these fit on top neatly because 1 plus 1 is 2. Welcome to the Oxford MAT Livestream. 1 plus 1 is 2. The other choices you can make, though, I think whenever you have a 2, you have to put a 1 and a 1 on top of it because that's the only way to split up 2 into numbers that are between 1 and 1 with, oh my goodness. So if n is 2, then this says 1 is less than or equal to your first number, and 1 plus the other number must be 2. So I guess those numbers really are 1 plus 1. But we haven't been asked about 2 towers, we've been asked about 4 towers. Still, it's nice to build these things up from small cases to larger cases, right? So 3, we could have k1 being 1 or 2 in that case. So we have 2 possibilities of forming here. 1 plus 2, exactly 2 other towers, so I have to put the second one on. And then on top of that 2 tower, this has to be not just a 2 brick, but a 2 tower. And the only 2 tower is this, so I should draw, I guess, all of that. Splitting 4 up then, we could put a 3 tower over here, which means I have to draw all of it. So I could draw this one, 3, 1, 2, 1, 1, plus a 1 brick. Or I could use the other 3 tower over here, which would be the one that's kind of left like this. 2, and then a bit here. I'm having fun with number 1. Or I could do the mirror image of those 2. So reflect those 2, because I could do 1 plus 3 instead of 3 plus 1. What's the maximum height of an n tower? Yes, it is. It's n, isn't it? Because, yeah. Ooh, the expansions of cosine x. You can integrate semicircles now. Fun times. Yeah, so drawing it would be impossible in this year's maths. But you could still ask parts of this question, couldn't you? Using typed responses. You could ask how many of the 4 towers are there. Maybe ask describe all of them or explain your answer or something. What's the maximum height of an n tower? Justify your answer is exactly something you can do with text only, right? Can you do this with a standard keyboard? Because it's 4 or n. n because, and then give some sort of reason for why the largest brick you can see in each row is at most 1 less than the brick below. So as you keep going, after n rows, you can't possibly have anything left because its maximum size will be 0. And also, you can do that. I guess those are 2 things that we should say. Can do it and can't do better. One way round shows that the maximum is at least as much as this, and the other way around shows that the maximum is at most this. Okay. Is it a bound? You can't get more than 2n. That's true, but not interesting. Or is it a kind of lower bound? You can do better than 1, which is a lower bound, but not interesting. Yeah, so it keeps going down by 1 as you go. At least 1 for the largest brick. I don't know if I've done every week, but I've done quite. We're trying our hardest to find an opportunity to. If I teach you nothing else, adding together small natural numbers. Speaking of, here's the area: 4 plus 4 plus 3 plus 2, which makes 13. So taking an n tower of maximum height, which you by this point have strong feelings about because you can do it, add up the the height of that thing. Which there's a trap here, isn't there? That the bottom 2 rows are both size n in area. So something like you have this pattern here, something like n plus n minus 1. And it stops at 2 because the 2 tower near the top has 2 1s on it, and then the 1 towers don't have any 1s on top of them. 2 at the end. Yes, there it is. ... 2. I like to write in. I agree with this in chat. I like to write in the last couple of terms just to remind myself what the pattern is near this end as well. But yeah. That's not like for marks. That's just for me keeping track of what I'm doing. We have over 9,000 subscribers. We've built them up slowly over the years. Most of our 9,000 subscribers are now at university, I think. probably. That's not a stat I actually know, but so probably most of our subscribers are not coming back to watch the MAT live stream every year, but yeah, I was pleased that we hit 9,000. Good. Which I think we did a couple of weeks ago. Good. What are we doing? Oh, infinitely many n, such that this part is impossible to read, isn't it? Show that there are infinitely many n. I'm with you so far. I know infinitely many numbers. Such that there is an n tower. Yep, already drawn one. Already drawn an n tower of height n. Very good. Of height exactly. And then they give me this expression with logarithms in, which for n equals 5 isn't even a whole number. So I guess I would like that to be a whole number. That's maybe the first thing you think when you see this, is sort of, how could it possibly have height 1 plus log 2n? I mean, maybe the first thing that you think is, aha, I already have examples, infinitely many examples, where the height was n exactly. Because I had these ones of maximum height. Maybe n is equal to 1 plus log 2n, but no, it's not. Those things are not equal at all. So yeah, n's got to be a power of 2 in order for this question to make sense. So we should try at least. What am I writing? Try n equals 2 to the k. And then our challenge is to find something of height k plus 1, which sounds large because I have a k, and now I want height k plus 1. But actually the n that I'm working with is enormous. It's some enormous power of 2. Yep, and in chat there, anonymous person has already told us how to do it. It's the first thing that I would think of. We drew some pictures up here as well. Let's say first thing I think of. First thing to try. I think we drew one of 4 is a power of 2, and we found this kind of interesting tower. It was actually the tower of minimum height, but that's not part of the question. Is it harder to prove that? Huh. It's harder to prove that. Not impossible, but not impossible for a math question, but it's harder to prove that. Yeah, okay, extension question, if you're interested. I think that that's the minimum height. When n is 2 to the k, I think the minimum height is 1 plus log 2n. I think that quite strongly, but proving it in a convincing manner is a task for you at home, if you can. It's not part of this question, you don't get any marks for it. But there again, this is a past paper question, so none of us are getting any marks today. Right, what am I talking about? Oh yeah, height k plus 1. So this turns out to work. 4 is 2 squared, and it has height 3, and the pattern just continues. If you want 8, put 2 of these on top of an 8 brick, and then the height goes up by 1, the power goes up by 1, everything's fine. Yeah, keep halving it. Oh, sorry, somebody in chat did do math in 2018, and is still here on the MAT live stream. There you go. Just after I said that people don't hang around. Proof by induction works, but it's also just directly. You could just describe the tower, halving every row, and that just works directly, I think. Size halves. Which is less than n minus 1. Yeah, it's kind of that's a kind of a greedy algorithm. Maths 2 to 2 to 2. It's the thing that I'm worried about. You make the size, you make the maximum size small quickly, but then maybe you fall into this trap where a small number has lots of fiddly bits on top, whereas a middle-sized number would have let you go to 0 faster. It turns out, I think, that greedily making the number small, haha, I'm going to go small numbers, and you just make them small as possible, in some sense, then that works, and you get to 0 really quickly. But I could maybe come up with a separate question where that's a trap, which would then be too hard for maths, because... Anyway, never mind. We have the number of towers. Oh, okay, we're going to make a formula for the number of towers in terms of the number of smaller towers. I guess you have a left tower. of size k1, and you have a right tower of size k2, and you know those have to add up to n. So you want something like, so t1 is 1, but I'll humour them by writing t1. So this could be 1 and n minus 1, or they could be 2 and n minus 2. The rules are that they have to add up to n, and so on. I guess they should go all the way up to n. Oh, no, it can't be n, because the other one has to be, can't be 0. So the kind of limit here is not this one, n minus 1 and n minus 2. Okay, and then so I've got lots of choices, and independently I've got lots of choices for the one on the right. I can make those choices independently in each case, and then I should add all of these cases together. So I think the hard part in terms of explaining this is to explain why I'm doing this combination of adding and multiplying. You know, sometimes you multiply choices together if you're making independent choices sequentially, and sometimes you add if you're making mutually exclusive, choosing between mutually exclusive options. What's the size of my left tower is mutually exclusive. My left tower is one of these things, and so I'm adding those cases. But then once I've chosen the size of my left tower, I have lots of independent choices for which left tower is it and which right tower is it. Oh, I'm mirrored, so this is left. Which left tower should I use? Which left tower should I use, and which right tower should I use? And I multiply those because lots of combinations from picking whichever left tower I like and whichever right tower I like. Good. Okay. Compute T6. So I guess this says something like you need to know lots of previous values in order to work these things out, and you get a sequence called the Catalan numbers, which I like a lot. I'm not responsible for this question, but I love Catalan numbers. I've got a whole book about Catalan numbers where the answer is always Catalan numbers. I don't know if this question is in there. It probably is, because come on, Catalan numbers. Oh, and finally, show that Tn is odd if and only if T2n is odd. Odds and evens. Yeah, odds and evens. So if n is even, then you get lots of repeated terms. Is that true? Oh, you get lots of repeated terms anyway, because these things are repeated. The interesting thing you get is if n is even, you have this kind of Tn over 2 term in the middle, and then whether or not that's even depends on whether Tn over 2 was even or not. So if that one is odd, then you have loads of doubled up terms plus this odd square. And if that was even, then you have loads of even terms plus this thing. So if and only if, I think this square number is odd if Tn over 2 is odd, and it's even if Tn over 2 is even, and its parity controls the parity of Tn, because everything else in there appears twice. Good. It's a bit like a geometric series, but oddly not quite. Not quite, but close. But yeah, it's weird. Depends on all the previous terms in this kind of combination way. Somebody has helpfully pasted lots of Catalan numbers into chat, which Callie has approved as a chat message, even though it's just a long string of numbers, because we like that sort of thing. 1125, 1442. Yeah, 42's in there as well. The first ones are like that because, let me demonstrate. Okay, I'm going to skip that opportunity to tell you that 1 plus 1 is 2. Yeah, how many of these people are doing that? Right, 20 minutes to go. I think I've done questions that people requested. I'm sorry if I missed. There are only a few requested, so sorry to 25% of the requests that I might have forgotten about. I thought about talking about some hard short questions like this one. I thought we could just sort of knock a couple of these over in the last quarter of an hour here. I don't know how you feel about that. Maybe you've had a chance to try this question. It's from 2018. It's hideous. Look at that. Look at that x to the 8. Ugh. Let's zoom in a little bit more. There we go. That's as close as I dare get. X to the 8 plus 4y x to the 6 plus 6y squared x to the 4 plus 4y cubed x squared plus y to the 4. Suggestions in chat. What on earth do we do with that? Once you see it, you can't unsee it. Once you spot the kind of pattern to what's going on here with those terms inside the bracket, you can't unsee it. For me, it's maybe the 14641 or just the 464 pattern. I've seen 464 before, or maybe it's the powers. These terms are written in the correct order, I think. Those y powers go y squared, y cubed, y to the 4. I've seen a load of things like that. That's polynomial in y, but at the same time, the x powers are going down, x to the 8, x to the 6, x to the 4, x squared, and so on. So almost want to divide both sides by x to the 16 or something. Not a huge amount, but a little bit. I want to divide both sides by x to the 16. I'm saying 16 because of the awkward squared over here. Maybe I should just write. Should we just delete that and put like a plus or minus 1 over here? That's better, isn't it? That's nicer. Because then it'll square to 1, so that's fine. We only need 2 solutions. Binomially condense it. That's a great phrase. Yeah, people have spotted the binomial, that this is in disguise x squared plus y to the power of 4. This guy plus or minus 1, and I now reckon that it's probably plus 1, because that power of 4 is not going to be negative 1, is it? So we're looking at x squared plus y is, well, I suppose it's up inside here. So this is to the power of 4 is not minus 1, but then the thing inside the brackets might be plus or minus 1 because those things both raised to the power of 4 give you 1. There's that awkward thing about minus 1 to the power of stuff. We've talked about it before, that minus 1 to the n is a slightly interesting function of n is 1, 2, 3, 4. It goes backwards and forwards. So it introduces these kind of even and odd patterns, if you like. Anyway, x squared plus y equals plus or minus 1. That's a pair of quadratics, isn't it? I feel I may have dropped a minus sign somewhere. Maybe not. Yeah, minus 1 on both sides. Yeah, I don't know about it. Yeah, okay. Must be symmetrical about both the x-axis and the y-axis. So I agree with that. It depends what sort of symmetry you mean, doesn't it? I agree that x, replacing x with minus x, which is a reflection in the y-axis, I agree that it needs that symmetry. You know, I think I've got this wrong. I can't immediately see where I've got it wrong, but I think I have. I'm going to be very sneaky. Will this appear on the correct monitor? Maybe this will be nice to me and appear on that monitor. Oh, it's thinking. It's open on the correct monitor. Ha ha ha. Now no one will know that I looked up the solutions. Ha ha. I just feel like I've done this before and got a different answer. Nope, I've done it before and got the same answer. Cool. Yeah, so y is plus or minus 1 minus x squared, which is this one over here. I guess I could have just asked chat. I could have just asked you. I got 2 sad quadratics. Maths question mark has a question. Yeah. Ooh, what is that? X squared plus y squared minus 1. X squared plus y squared plus 1. Oh, because difference of 2 squares. Yes, difference of 2 squares. But I think probably easier to, well, okay, so difference of 2 squares. So I'm reading this anonymous chat message, I'm just going to highlight. I think it's true. I see what you've done. You've done difference of 2 squares. You saw the 4th power, that's a square. You saw 1, you thought that was a square. You did difference of 2 squares. I've got a lot of time for difference of 2 squares. You can then notice that this bit, does the highlight show? Yes, it does. This bit's positive because it's a square plus 1. So that was non-zero. You may divide by it, and then you get down to this bit, which is the difference of 2 squares again. So I think I'm a big fan of difference of 2 squares, and you get the chance to do it twice. So you should go do it twice. That'll be very, very entertaining. But yeah, to get there, maybe you need the hint that you can divide by this bracket. Okay, good, right. Big fan of difference to two squares. I don't know why that's hands up. You got me. I love difference to two squares. Yeah. What's the suggestion? A squared minus use a squared minus b squared as difference to two squares. Good. Yes, you can highlight as well. This one. Yes. I suppose maybe that's the same person. Yes, that's the same person, isn't it? They're telling me what they're going to do. Oh, where's it gone? They're telling me what they're going to do, and then they're doing it. Yep, good. Aha. Sometimes I can work out the anonymous people are the same person. Sometimes I believe that all of the anonymous people are the same person. One hive mind of a hive mind of anonymity. Right. Okay. I thought about talking about J, but that one's a bit complicated. J is susceptible to some sort of symmetry argument. So the question wants you to imagine taking all sorts of polynomials, p, and drawing p of x plus p of y equals 0. And you can make one of these pictures, but only one of them. Have I got a Desmos for this? I don't think I do. I should make a Desmos for this. We're going to quickly make a Desmos for this. The Desmos for this would be something like you're imagining all polynomials. Let's do it in a cubic, that sounds fun. Cx plus d, imagining all polynomials and finding all the points with p of x plus p of y equals 0, which as you change a, b, c and d to think about all possible polynomials, woo, it does all sorts of stuff. There it goes. Is it going to do it again? Yeah, so it does all these sort of weird things. See if I can make it do that bit with the interesting topology again. There it is. So there's all sorts of weird stuff in general. So there's probably some hard questions you can ask about what sort of shapes and topology you get out of things where you throw a random polynomial in here and you look at the behavior of these points. That's so cool. Special case where it's perfectly aligned. Yep, good. Right, okay, I've distracted myself. We're supposed to be thinking about this. Did you notice any fun symmetries? Obviously, in the test, you don't get to play around with Desmos, but maybe you spotted some symmetries. Maybe you spotted some things like this. Yeah, so 0 and 1 degree, I think, are allowed. 0 degree is not very fun because the 0 degree polynomial is just, that's something that people say for the constant 0 polynomial, which, yeah, it's not that great, is it? It just gives you 0 equals 0. So that's true for all values of x and y. Colour in the entire plane. Constant polynomials, though, you can do some stuff with that. You can do some damage there, can't you? If p of x is just the constant x, not constant x, sorry. If p of x is just x, then you get x plus y equals 0, which is exactly d, isn't it? So we can make d. I'm happy. Oh, I see. The options are we can make multiple of these. I thought maybe we were done there. Question is, maybe can you make a circle? Can you draw a circle? Is that a Matt Parker quote? There is no equation for a triangle. Okay. Yeah, it is symmetrical on y equals x. Swapping x and y, which does mean reflection in the line y equals x. Maybe that's not obvious. It's not one of the ones that you're expected to be able to do to functions, really, I think. I guess we're swapping x and y. Geometrically, you had axes like this, and now they're the other way around. That's just going to flip them, isn't it? It's going to flip things. The line y equals x is the points which don't move under that. Yeah, so we definitely can't make a. We can't make a because we're flipping x and y. If you flip x and y, you should get another solution. If p of x plus p of y is good, then p of y plus p of x should also be 0. So you should be able to switch the coordinates around. That rules out a, which actually rules out, embarrassingly, perhaps rules out 4 of the options. So that means we could probably not make b and can make c, but you know. Yeah, polynomials are always finite degree. That's what polynomials are. Yeah, sensible definition of a polynomial is that it has finitely many terms. We've got an equation for a circle, haven't we? We know circles look like this, but I suppose that equals 1 on the right hand side. So it's a bit fun to try and remove that, and you have to remove it in quite a symmetric way. You have to remove the 1 on the right hand side. I want 0 on the right hand side, but you can remove it in this kind of symmetric way to give you a polynomial. That's a polynomial, right? X squared minus 1/2. Seen nicer polynomials, but that is a polynomial, so I can make C. We've decided we can make D. Something we don't really have to engage with for the question is the fact that we can't make B. There is no equation of this form for a triangle. Don't really have to engage with it. So something you could say is that looking at this side of the triangle, there are values here where P of x takes some value along here, along this line x equals constant. P of x is constant. P of y has to be negative that constant. In some region. So we'll negative that bit in some region, and then not that on the other outside that region, but not that outside the region. Polynomials don't do that. If you translate this by a constant up and down, you get to a situation where your polynomial would have to have zeros all the way between that region, so it had points all the way between, but it doesn't happen. I think you can get quite close to B. I'm not sure. This is a Matt Parker video, maybe, the one people talk about in chat, where you can get quite close to a triangle. If you'll accept rounded corners and slightly curved edges, then this line might not be x equals constant. So, yeah. Chat's now thinking about this. Why isn't A possible? Because over here, this point, let's call it 1, just for sake of argument. This point shows you that P of 1 plus P of 0 is equal to 0, but the absence of this point shows you that P of 0 plus P of 1 is supposed to be not 0. That is a problem. You know, I should be able to switch around between the x bit and the y bit. It should have that symmetry to say, once you've found a point where x and y work, I should be able to flip them, because then I've got P of y plus P of x. On the one hand, P of 1 plus P of 0 should be 0. On the other hand, it's suspiciously non-zero. Good. Could you do P of x times P of y to make a triangle? I think probably not. Probably not. Yeah, you're going to run into so much trouble, aren't you? Because some of those things will be 0, and then they'll be awkwardly 0 along a whole line or something irritating. I suppose option C doesn't have any lines in it. Maybe I should go back to playing around with this in Desmos, right? Maybe we should try and find other stuff. Right. Oh, is exit. You're supposed to have a minus a line of symmetry. Oh, I'm not sure. I think it depends whether you have an even polynomial or not. Definitely, I had examples in Desmos that didn't have the other symmetry. Oh, look at all my programs. I had examples in Desmos that don't have symmetry in the line y equals minus x. They have symmetry in the line y equals x. Like that, binary symmetry, but not that one. So I think it depends on the degree of or it depends on the symmetries of the polynomial. Okay. Yeah, so people know in chat, this is the awkward thing. People know this equation for a square, right? Maybe you've seen this before. Let's get rid of that for a bit. Oh no, I sort of liked that. Can I have it back? Yeah, good. Okay. Maybe you know this equation for a square, which is like not quite a square because it's got rounded corners. But you have to really zoom in, and slightly curved sides. and that is of the format polynomial in the same way that we did the circle. Polynomial plus polynomial in y equals 0. I mean, it has these kind of straight sides that I'm trying to say are not possible. So I think I should look over there for. I can't remember what happens if you put an odd number in. Oh, we did this as a question once, I think. I think something's pretty close to being a triangle. It's got three sides. It's got three corners. It's got three sides. One of the sides is infinitely long and wraps around through infinity, but you know, looks a bit like a triangle. Yeah, I'm out of ideas, I think. I don't know how to make that more triangular. I'll do the difference between that and x to the 97 or something. Minus the wide stuff as well. Maybe this doesn't do anything. That didn't really do anything. I don't know what I expected. Add them? Even? The important thing is that I'm having fun. Yeah, I'm not doing anything, am I? This is having less than no effect. I've got to do it to both. Right. Oh, I have machinery for this. I should be changing p of x. Right, okay, not now. Yeah, if you restrict the range, then you can get that. Okay, advice for those who consider a gap year. Let's do some advice quickly. If you're doing a gap year, then you should probably plan something. My advice to you as someone planning a year out is to think about what you're doing for your maths, to keep your math skills sharp, because tutors aren't admitting you to start immediately, they're admitting you to start in roughly a year. So they want to be confident that when you start following your gap year, that you'll also be ready to start. This is actually true for everyone. I'd like to know that you'd be ready to start the course in roughly a year's time. We make offers in January, right? People start later on. Usually it's because we know that they're going to be finishing off their school leaving qualifications. If you're outside of school because you finish your qualifications, then having something else to do is probably a good idea to keep your skills sharp. Love doing maths for fun, then you find other sorts of maths. As I always say, it hardly matters what the sorts of maths are, so long as you find maths problems that you can't do straight away. You might like to look at some university maths, but I wouldn't try to learn university maths self-teaching it because it's really hard. Good. Okay, I think I've done the questions that I wanted to talk about. Oh, I didn't do that one. Let's do that one really quickly. Just because we can. I'll do this one while talking. Are there any more admissions questions in chat? Not sure. There's that Desmos question. Yeah, symmetries. There's some symmetry over there. This was 2018 question 1b. The idea is that you take this function and you check whether or not it satisfies this differential equation. I'm pretty happy with this question because it's the first MAT question I wrote. I've written a few, and this is certainly one of them. So if you do all the differentiation, I think I might have done the derivative every time there, rather than doing the sensible thing of working them out first. You know, pre-compute and then substitute. What was that? There we go. I've definitely got too much stuff inside this Desmos, inside this Miro board. K squared. The thing the question does, come on. Almost there, Miro. We can do it. Miro is the name of the whiteboard. Almost there. If you plug everything in, then you get exponentials everywhere, but they all cancel, so it's nice. And you get an expression like this, which has solutions k equals 0 for k squared equals, there's a difference of 2 squares here, it's 2, so k is 0 or root 2 or minus root 2. And they all count. So there's 3 of them. I think lots of people missed the 0 because either they divided both sides by k without thinking about 0, or maybe they thought that if k equals 0, then this isn't really a function, and it is a function. It's 0 on both sides because y is just 1 if k equals 0, but that's a function. maybe not my favourite function. I wonder what my favourite function is. If I said what my favourite function is on record, can I just do that? Yeah, so someone in chat wants to use high-powered math. They want to use a Laplace transform, and you really cannot use a Laplace transform on this question. The joke is that you're kind of almost doing a Laplace transform by following the instructions, right? You're plugging in e to the kx, which resembles this high-powered technique called Laplace transforms. But knowing about Laplace transforms, I think almost makes you worse at doing the question, because you might try and do a Laplace transform to it. Hey, don't do that. Does it make a difference if you put a comma and or? Does it make a difference if you put a comma and or in between quadratic solutions? No. I wouldn't put the word and, because I think that's logically incorrect. I'm not saying that k equals 0 and k equals root 2. That'd be nuts. There are no such values of k where k is 0 and root 2. But if I was writing a sentence, then I suppose I might write the solutions are k equals 0 and maybe. I tried to avoid it, I think, but just it's good for you to remember that they're alternatives rather than simultaneously true facts. Maybe you will write commas from now on to avoid this. I try to write or. Look, my handwriting's bad, so neither of those look like the word or, but I'm trying to write or. Right. What's my opinion on Terence T. Howard saying 1 times 1 is 2? My opinion is that they may be going for the fact 1 plus 1 is 2, a fact that we have on the maths live stream quite a lot. I've not heard of this. Is it a kind of philosophy thing? Or do they just want a kind of different sort of multiplication? Terence T. Howard is, as far as I can tell, an American actor, not a philosopher. Maybe also a philosopher. You can be both. Okay. Anna's off, and so am I. Are there taster lectures? Yeah. Okay, so the stats talk is kind of a taster lecture. The philosophy talk is kind of a taster lecture. Maths at Oxford is just an introduction to the course and admissions process with me. So sort of taster lectures. But for the September open day, we know that people are mostly here to look at colleges and to get information about how to apply, because lots of people are about to apply. Right, see you around, everyone. Take care. I will see you in 168 hours for another episode of the Oxford MAT Livestream. Yes. Bye.